Okay, so I think now it's time to start our session. So thank you very much for attending our session. This is today's session title. So today, we are going to talk about the streamlined Baremetal deployment, a journey of custom controller integrated with OpenStack. So in this session, we will talk about our technical challenges and also problems which we tackled, and also how we solve the issue during the resolving of our encountered issue. I'm Mitsuhiro Tanino, Senior Software Engineer from the LI Corporation, and he's Kuroha, also from the LI Corporation. So let us start from the self-introduction at first. So again, I'm Mitsuhiro Tanino, Senior Software Engineer of the LI Corporation. So I have working on the LI Corporation for a few years, and I have contributed to the OpenStack Shinda project. And also, I have contributed to the Kubernetes SIG storage, I think more than 7 or 8 years ago. And now I'm a senior software engineer working as a platform engineer, and we are operating the huge scale OpenStack cloud environment as a private cloud. So next.
Hello, I'm Masanori Kuroha. I'm also a software engineer in LI Corporation. I operate and develop large-scale IaaS system using OpenStack. Now let's move on to today's agenda.
Okay, so today we will share about these 4 agendas. So first one is introduction of our service and the private cloud used in the former LINE Corporation and also the former Yahoo Japan. And also second, we will share the requirements for providing the Baremetal server in new private cloud. After integrating the corporation, we are building the new private cloud. And at third, we will share our former Baremetal server management architecture issue and look back what kind of the issue was there in the former architecture due to the large scale. And finally, we will share our new journey to streamlined Baremetal deployment architecture overview and how we utilize custom controller with Kubernetes on our Baremetal server deployment environment. Okay, so let's start. So first section is the introduction of our service and the private cloud. For the LINE company, a former LINE company, we provide the communication upline and associated many services. And these services are launched on the private cloud code builder that is shown in the right side. So in builder, we provide many services, PaaS layer services, or managed services, IaaS services. So in the PaaS, in the managed service environment, we provide the Kubernetes environment or MySQL service, etc. And also in the IaaS layers, we actively using the OpenStack environment, and we already provide the huge scale private cloud using the OpenStack environment. And next is Yahoo Japan's private cloud environment. So Yahoo Japan provides portals or search or e-commerce, such kind of many services on top of the private cloud IaaS layer. And similar to the LINE environment, Yahoo Japan's private cloud also running on the huge scale OpenStack environment. So both of the company using the huge OpenStack private cloud environment. And now, we integrated the LINE and Yahoo Japan. Then we are developing the new private cloud environment similar to the on top of OpenStack and Kubernetes. So this table shows our private cloud scale on the LINE builder and also the Yahoo Japan. On the right side. So we provide more than 11,000 hypervisors and more than 130,000 virtual machines and more than 24,000 Baremetal servers on LINE side. And on the Yahoo Japan side, we provide more than 27 hypervisors or more than 220 virtual machines, 200 1,000 virtual machines, and also the more than 73,000 physical machines. So as you can see from these values, so we are providing the very, very huge scale of private cloud environment. And in order to operate this kind of the huge scale environment, so the kind of the manual operation or insufficient operation is not permissive. That's why so we hit the issue of the bare metal deployment architecture. So that is today's session topic. So next, I'd like to explain the requirement for providing a bare metal server in our new private cloud. So as for the background, so the integration with the LINE and Yahoo Japan happened, and after that, so we started to develop the new private cloud environment called Forever. That is the logo mark of the right side. And in the Forever, so we aim to provide the user friendliness or productivity, high performance, and high availability, and also the cost efficiency and the private cloud security. And one of the important topic to provide the new private cloud is that we try to aim the providing the unified IaaS offering for VM and bare metal. So it means we aim to offer the consistent set of the functionality for both virtual machine and the bare metal server, so that the end user can use the similar feeling for the VM case and also the bare metal case. That is a very benefit for the end user. And from the end user perspective for the Forever, so we thought there are five major requirements for the new cloud environment. One is user friendliness. So end user would like to use the new cloud as an easy-to-use interface or create resources by few clicks, or as for the productivity, features and tools for the self-automation and self-management and automation are required. And high available perspective, so we try to provide the multi-available zone and supports the reliability for the private cloud. And the cost efficient and the security, we provide the cloud security via the virtual private cloud and also the IAM and data protection. They are the requirements which we consider for the user perspective. And from the cloud operator perspective for the new cloud, we consider these 3 points are important to develop the new cloud. So first one is scalability. So we need, as we shared the number of our cloud environments, so we need to operate a huge number of the servers, hypervisors. So scalability, manage the large-scale server deployments from 1,000 to 10,000 servers. That is an important topic. And also the efficiency, so cloud we need to provide the efficient management through optimal resource allocation. And third one is reduce operation burden. So operator need to operate the cloud environment easily. These things are main key aspects from the cloud operator. And today, so we'll focus on the cloud operator's perspective in this session. So next section, so we'll share the former bare metal architecture issue and how we tackle and what kind of the issue was there. This is the former bare metal management architecture, and right side is a bit a complicated figure, but as you can see in the blue box, so bottom side is the bare metal server, and in the OpenStack environment, one Nova compute service manages the one bare metal compute. So it means one-to-one mapping was there in order to manage the bare metal server. So this architecture provides a precise control between the bare metal server and also the Nova compute. But in order to scale up the bare metal number of the bare metal server, like the 1,000 or 10,000, it means similar number of the Nova bare metal compute pod or deployment, config map, or replica set are required. So it means we need to provide a huge scale cloud Kubernetes environment in order to manage the bare metal server itself. So gradually, so this architecture hits the scale issue. And also, in order to manage the Baremetal deployment to cloud with OpenStack, so second point, so it requires an OpenStack data setting to Nova, like the OpenStack Nova flavor. It's creating the resource profiles for the new server capabilities, or OpenStack Nova aggregate, which is a logical host group integrated in the OpenStack. Such kind of the data source registration are required for the integration with the Kubernetes and OpenStack environment. So this is the former Baremetal deployment operation flow from the cloud operator perspective. So there are 4 major steps. So as you can see, so that the first steps, that is normal operation. So cloud operator just make a pull request in order to add the new servers as a Git repo. Then once the PR is merged, second step is ArgoCD automatically fetches the information from the Git repo so that the ArgoCD made a deployment job onto the Kubernetes. And then on the third steps, inside the Kubernetes environment, cron job actually deploys resources like the Nova compute or deployment of the Nova compute, replica set, and config map secret into the Kubernetes environment automatically. Then finally, on the step 4, ArgoCD cron job also need to deploy the information into the OpenStack environment by using the Ansible OpenStack module, so that the Nova aggregate information or the flavor information, aggregate information or the location flavor, such kind of the information registered into the OpenStack environment. And finally, the Baremetal server is available to use. These kind of the steps are required on the former Baremetal deployment. But gradually, so due to the increasing of the rapid scale, so this operation takes much time. So here is a summary of the issue at the Baremetal former deployment architecture. So there are 3 major issues which we observed in the previous Baremetal deployment architecture. The first one, so the escalating deployment time. So we started to provide the Baremetal server around the 100 or 500, but gradually the number of the server increased to the 10,000, and finally it reached to the 6,000. And in order, due to this kind of the linearly increasing the number of the Baremetal Nova compute, how the information into the Nova aggregate or increasing time for the deployment, 1,000 config map or 1,000 of the deployment replica set into the Kubernetes. Deployment time is gradually increasing. And finally, so in the recent situation, in order to deploy the information around the 6,000 Baremetal server into our cloud environment, it takes more than 2 hours. So just deploying the Baremetal server information into the cloud takes 2 hours, a little bit heavy operation for us. And so second one is resource under management insufficiency. So limited then, so as you may know, so the one worker node of the Kubernetes can launch on the 110 pods per worker. Therefore, in order to support the more than 6,000 Baremetal servers, Nova compute, we need to prepare around the 55 worker nodes to manage our Baremetal server. And this architecture is a little bit costly. And we need to prepare the 28 vCPU and the 56 gigabyte memory worker node in order to manage more than 6,000 pods. And finally, technical bottlenecks were there. So parallelization, we were limited by using the Ansible and the OpenStack integration. So the number of the Baremetal server are linearly increasing, but the deployment operation cannot efficiently improved. So as I said, so the deployment time were increasing linearly based on the increasing number of the Baremetal server. And also, this kind of the complexity make operator to hardly understand that environment. So that caused the increased operational complexity and also the cost for the IaaS operator. So during the rapid growth of the bare metal server, number of the bare metal server environment, so we hit this kind of the environment. So that's when we try to build up the new private cloud Flavor, so we try to resolve this kind of the issue by using the custom controller. So from now on, he will explain why we choose the custom controller and how we adapt the custom controller to deploy the bare metal server itself. Okay.
Okay. In this section, we will detail our new initiatives using custom controllers. First, let's talk about why we choose custom controllers. Let's reconfirm the main requirements for bare metal deployment. These requirements include scalability, which involves managing thousands to tens of thousands of servers, and reduced operational burden, allowing for rapid deployment and scaling through automation, and efficiency, which focuses on optimal resource allocation. The deployment system using custom controllers offers basic features that effectively addresses these needs. First, parallel and incremental deployment allows us to parallelize large-scale operations and deploy incrementally by event-driven process. The congestion loop automatically aligns the desired state with the actual state, minimizing manual intervention and reducing operational burden. Additionally, flexible definition enables us to customize CRDs and deployment logic, optimizing resource usage. Just because the requirements for bare metal deployment and the basic features of custom controllers align very well, we decided to adopt this technology. Next, this is an overview of the new bare metal deployment flow. First, the bare metal operator registers bare metal server information, which includes each server's hardware specs, project usage in GitHub repository. This is the same as before. When a pull request is merged, GitHub Actions is triggered, and custom resource manifests are automatically created and applied. This is a major change. The custom controller within the Kubernetes cluster constantly monitors for new creations or changes to this custom resource, and based on the detected changes in the custom resource, the custom controller executes necessary deployment process, such as creating Kubernetes resources and configuring OpenStack settings. In the new architecture, by transitioning to declarative management using custom resource, we aim to be free from the complexity of Ansible scripts and the bottlenecks of sequential execution. Let's take a closer look at the definition of custom resource, which is central to this flow. In the new architecture, bare metal servers are managed centrally using custom resources. This is an example part of a custom resource. Our CRD is defined on a per rack basis. This is because we define physical racks as failure domain to provide reliability for bare metal servers, intending to avoid rack-level hardware failures. In OpenStack as well, servers are logically grouped by rack, which aligns with this concept of failure domains. So designing the CRD on a per rack basis is an efficient approach that considers OpenStack's logical grouping. The definition for each server includes information necessary for OpenStack integrations, such as OpenStack flavor, which indicates the resource profile for server capability, and OpenStack project, which shows users of the server. In this example, you can see multiple servers belonging to a rack named named LAC-A defined in a list format. Next, we will explain the operation of the custom controller's reconciliation loop, which monitors these custom resources and performs the actual deployment processing. First, for each monitored custom resource, it creates one config map and one deployment. This config map contains settings for the novel compute process of each server, and the deployment uses this config map. Next is OpenStack configurations. It configures logical host groups named aggregates. Servers are logically grouped by LAC in OpenStack world. It also sets traits for each server. Each Baremetal server has a flavor trait indicating hardware specifications and a project trait indicating stock assignment. The diagram shows Baremetal servers logically grouped into LAC-A and LAC-B aggregates with flavor traits and project traits for each servers. Benefits derived from the controller's basic mechanism include incremental deployment by monitoring custom resource update events, and accelerated deployment is also achieved by parallelizing the reconciliation loop. This automatic configuration change to declarative state and parallel processing becomes the key to resolving the challenges of the new old architecture. Let's see specifically how this custom controller behavior leads to resource savings. In the previous architecture, the configuration was one Nova Compute container per pod. Although Nova Compute containers themselves do not require many resources, the per node port limitation made it hard to consolidate pods efficiently. As a result, more worker nodes than necessary were required. In the new architecture, the custom controller operates based on per rack custom resources, consolidating and launching Nova Compute containers for multiple servers within a single pod. Each rack can hold up to 40 servers, so this approach did reduce the number of config map and deployment resources by up to 1/40. Consequently, the number of worker nodes required to manage over 6,000 Baremetal servers, which was around 55 nodes in the previous architecture, was reduced to just 17 nodes in the new architecture, achieving a reduction of about 70%. This pod consolidation was a significant achievement in resource efficiency and cost reduction, resolving the insufficiency in the old architecture. In addition to resource savings, there is another improvement, the elimination of unnecessary Nova Compute restarts. In the old architecture, some configuration changes, such as stock assignment operations for specific end-user projects, would trigger a restart of all 6,000 Nova Compute pods, including those that did not actually need changes. This could potentially impact service delivery. Our improvement was to make Nova Compute restarts occur only when parameters within the relevant config map were actually updated. Specifically, we set the hash value of the config map in the annotation section. Since the Kubernetes deployment controller detects changes in pod templates and performs a rolling update, if there is no change in config map content, the hash value remains the same and pod recreation is not triggered. With this change, unnecessary Nova Compute pod restarts were reduced from over 6,000 to 0. This is an improvement that effectively uses standard Kubernetes mechanisms to resolve the operational issue and significantly enhancing system stability and reliability. So far, we have explain the main improvements of the new architecture. From the next slide, let's summarize how these improvements resolve the previous challenges. First, regarding the previous challenge of escalating deployment times. In the new architecture, the only manifests created externally are custom resources. And the custom controller rapidly generates config map and deployment manifests by directly using Kubernetes API, achieving faster speeds compared to methods using Ansible or Jinja 2 templates. Also, the controller detects and processes only added or modified custom resources. As a result, deployment time no longer depends on the total number of deployed servers. Next, resource and management inefficiency. In the new architecture, the consolidation of Nova Compute containers reduced the required number of worker nodes and resources. Additionally, the use of deployment annotations eliminated unnecessary restart of Nova Compute pods. These improvements brought significant benefits in terms of both operational costs and service stability. Finally, technical bottlenecks. In the new architecture, parallax CRDs and a parallelized reconciliation loop enable efficient and accelerated integration with OpenStack. The transition from sequential processing by external tools like Ansible to declarative event-driven processing by Kubernetes native controllers was key to resolve these bottlenecks. As a result of these improvements, let's introduce the current deployment status and expected deployment times with specific numbers. The new custom controller is already operational in Flowers production environment. Currently, 8 racks with 80 Baremetal servers are deployed and managed by this new controller. And 2,000 or 3,000 servers will be provided in this year. And here is a comparison of deployment times for over 6,000 Baremetal servers. Dramatic improvements was observed. For example, when adding 6,000 servers in one time, there is no previous result, but with the custom controller, it completes in about 50 minutes. Particularly noteworthy is the stock assignment for 6 servers, which involves changing the users of 6 servers. That previously took 2 hours and 40 minutes, now takes only 16 seconds with the custom controller. Similarly, adding 40 new servers, which previously took over 2 hours, now takes just over 5 minutes. And adding 400 new servers was reduced from over 2.3 hours to just over 8 minutes. These results clearly demonstrate how efficient the new architecture is and signify that the challenges we face have been improved. Finally, let me briefly introduce the current monitoring system for this new deployment system. In the Flower ES system, like many other components, Kubernetes status is also monitored by Prometheus. Alerts are routed by Alert Manager and notify operators through the PagerDuty app and Slack. The diagram shows an overview of the monitoring technology stack. For Baremetal-related issues, for example, if a specific Nova Compute container within a pod fails to start, it is detected as deployment replica sets mismatch. Also, if a specific Kubernetes worker node experiences high CPU utilization, it is detected as node CPU high load average. This monitoring system supports the stable operation of the new architecture. This concludes our presentation. Thank you very much.
Yeah, thank you for attending the session. So I think we have 1 minute. So if there is a question, please let us know. Go ahead. over there.
Just a quick question.
Yeah.
Have you considered cross-plane?
Cross-plane.
Yeah, because what you're doing looks like you're mixing two worlds, right? So you have Kubernetes world and OpenStack Nova. Nova is a virtual machine manager in
Yes.
OpenStack, right? So you're mapping Kubernetes objects to the Nova, and then you create the machines, and then you use them to create another clusters and so on. So this looks really like crossplane, because crossplane is basically the connector between Kubernetes world and something else, right? So you could extend crossplane and basically have the same result.
I see. Yeah, actually, so we haven't, investigated about the cross-plane, but we already have the strong OpenStack environment and also the Kubernetes environment individually. So, yeah, now we are using the integrated with the OpenStack and the Kubernetes, but we haven't used it.
Okay. Yeah, you could have kind of also tried to do the same with the Terraform provider for the OpenStack and control it from somewhere else. So it's the same, like a question of merging two worlds, which is one Kubernetes world and one Nova, right?
Yeah.
Right. Thank you.
Thank you.
Thank you very much for the presentation. Are you using any Redfish integration to control the servers?
Sorry, can you?
Redfish, the Redfish REST API for the BMC controllers.
REST API.
REST.
Yes.
Redfish.
So in the OpenStack environment, so the network communication happens via the REST API. So through the OpenStack environment, so we are using REST API. Is that a question for you?
No.
Oh, sorry. Okay, I see. So, yeah, on the hardware layer, so we are using the kind of the software which directly manages to the IPMI layer in order to run the, let's say, Pixie boot or IPMI server stop or server stop or start. So, yeah, we have own developed software in our environment.
Thank you.
Thank you. Sorry, yeah, it's time. Thank you for attending our session.
Thank you.